Hello everyone. So today we're going to continue on 13.1. So last video we get to talk about what happens if we have an complex eigenvalue, and when we have a complex eigenvalue it usually results in a complex eigenvectors. And so now we have our solution. The only problem is in this solution we have a complex exponential e to the 1 plus it and e to the 1 minus it. So what we're going to try to do is try to figure out how to rewrite that properly into sine and cosine function, which is what we think is going to happen. So let's go and give it a try. So therefore, this would equal to C1, e to the 1 plus it would actually turn to e to the t cosine t plus I e to the t sine t. So that's what e to the 1 plus it turn into. And that get multiplied by 1 negative I plus C2 e to 1 minus it would turn into e to t cosine t minus I e to t sine t. So this sometimes you can get confused of why is that, and because this tends to come out to be e to t cosine negative t plus I sine t, e to t sine negative t. The problem is that cosine negative t is just cosine t, while sine negative t is actually negative sine t. So that's the reason why I turn into that. So now we can try to figure out what's going on with this. So first of all, notice that e to t can now be factored out. So I'm going to factor out, and I'm going to actually move over a little bit so that I have more room. So it'll be C1 e to t. And then what I have would be cosine t plus I sine t, because I multiplied that by 1. And if I take cosine t plus I sine t multiplied by negative I, become negative I cosine t minus I square sine t plus C2 e to t. And then what I have will be cosine t minus I sine t multiply, and the bottom one will be I cosine t minus I square sine t. So here the tricky part is that I square actually become negative 1, so therefore minus I square t actually become plus sine t, and this one also become plus sine t. So therefore, what I have would be this. So now the tricky part is to make sure you write the complex number in the correct form. And what do I mean by the correct form? Real component go first, imaginary goes next. So therefore, what I need to do is write the first parenthesis to be cosine t plus I sine t, and the bottom becomes sine t minus I cosine t, plus C2 e to t. So top stays the same, cosine t minus I sine t. The bottom have to be written as sine t plus I cosine t. So that still look a little complex, and as if you think about it, is essentially just have basically two terms involved: e to the t cosine t and e to the t sine t. Those are the only two terms that should remain, because remember what we have is a dimension 2 system. So therefore we should only have two terms. So right now our expression is not condensed and way too many terms. So what I'm going to do is expand them out. So therefore what I have will be C1 e to t cosine t plus C1 I guess I'll write the I in front. I C1 e to the t sine t plus C2 e to t cosine t minus I C2 e to t sine t. So I simply multiply everything out to the top. And then a second, the bottom one will be C1 e to t sine t minus I C1 e to t cosine t plus C2 e to t sine t plus I C2 e to t cosine t. So now it's just a matter of now combining things together. So if I look at the e to t cosine t, I notice I actually have c1 plus c2 times e to t cosine t. And then for the e to t sine t, what I have is I guess I would say plus I c1 minus c2 e to the t sine t. For the bottom, if I look at the real components, well, actually, I'm going to line up the e to t cosine t instead. So if I look at the bottom, I would have negative I c1 plus I c2 in parentheses e to the t cosine t plus c1 plus c2 e to the t sine t. Good so far. Now, something interesting right here. This particular coefficient, I'm going to factor out a negative I. And if I do that, I actually have c1 minus c2. So note that that kind of mirror this coefficient, and c1 plus c2 kind of match this one right here. So what I'm going to do is I'm going to do a little switching out our coefficient. I'm going to go and let, let's say d1 equal to c1 plus c2. And we're going to let d2 equal to, how about I times c1 minus c2. And so by doing so, allow me to now rewrite my solution into probably the most condensed form. Is d1 e to t cosine t plus d2 e to t sine t for my first one. My second one, this is negative I, so become negative d2 e to t cosine t plus d1 e to t sine t. So that form our solution. And you could write it many different ways. I don't have any particular preference in writing this. You can write it this way. E to t cosine t times d1 negative d2 plus e to t sine t times d2 d1. If you want, you could also collect the d1 and d2 together. If you do that, you can say it's d1 multiplied by e to t cosine t e to t sine t plus d2 multiplied by e to t sine t and negative e to t cosine t. So either of these ways would probably work. It's really depending on what you want to focus on. If you want to focus on just the coefficient d1 and d2, this is probably the best way to write it. If you want to focus on e to t cosine t and e to t sine t, the top way is probably better. All right. So I'm just going to box in this one for an answer because that's the last thing I write. So that's that. So notice that it still come out to be two terms when you have complex eigenvalue and eigenvector, but you would definitely take some time to get the expression down to its most simplified form where you only have two different terms, e to t cosine t and e to t sine t. All right. Now notice one of the things that we still won't be able to do is to deal with repeated eigenvalue. So that actually going to be something that we're not going to be able to do. Whenever we have a repeated eigenvalue, we're going to need to use another method to solve it. So that will be, we will talk about a different method in 13.2, obviously. So the next thing I want to do is to do the following. So now what I want to do is kind of generalize this concept and hopefully give you a much more constructive way to do finding a solution. So this is how it goes. So if we want to have an initial value problem, we can definitely solve for the arbitrary constant, like in this case, d1 and d2. So the way to solve that is actually quite easy. We kind of think about what we try to do. So here is how we're going to do it. So if we assume, let's say, if we assume that the eigenvalue for whatever differential equation or eigenvector, the eigenvector u1 to un of an n by n matrix A are linearly independent. That also meaning kind of implied that we have no repeated eigenvalue also. We can calculate the arbitrary constant, oops, missing a B, using the following procedure. So this procedure will allow us to actually solve a system of differential equation using eigenvalue and eigenvector properly. So what is this procedure? Start with number one. We're going to go and let capital U, so this is a capital U, be the matrix. So remember, we use capital letter to represent matrices. So let's capital U be the matrix with columns. Vectors. So very important, you're using them as column. U1, U2, to UN. In whatever order that we choose. But once we choose that order, we're going to have to be consistent with that order in a fixed order. This matrix U is called the eigenvector matrix. Of the system. And it makes sense because it's simply formed by just using all the eigenvector. So it's called the eigenvector matrix. And the important part is to make sure you understand is that we use the eigenvector as columns. And you have to pick some kind of order for them. The order that you choose does not matter as long as you are consistent with the order that you choose. Okay? So now once we have the eigenvector matrix, now let's do a second matrix, which is often referred to as the eigenvalue matrix. Let lambda t, so this is the capital letter lambda, I believe, sub t, be the diagonal matrix and it is defined as follows. So this lambda sub t matrix, the t in this case is basically the variable t. And this diagonal matrix, what does it mean by diagonal matrix? A diagonal matrix is basically a matrix that has 0 everywhere except along the diagonal, the main diagonal. So the main diagonal actually will be this, e to the lambda 1t, 0, to 0, 0, e to the lambda 2t, to 0. So this pattern go on. To e to the lambda nt. So that would be what we call the lambda t matrix. And of course, in this matrix right here, we need lambda 1, lambda 2, to lambda n in the same order, as established in step 1. so that they can be correspond together. So that's is a diagonal matrix. I'm hesitant to call it an eigenvalue matrix because it's not just the eigenvalue, it's a e to the eigenvalue times t matrix. So we just gonna call it lambda sub t matrix. Okay. Now finally, we can let C, vector C, be an arbitrary constant column vector. So what does this column vector do? Well, this column vector is basically going to be all the constants C1, C2, and so on and so forth connect together with entries C1, C2, dot 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 to Cn. And when we have that, we can now actually use that to write the general solution to our system, believe it or not. Okay, so the idea is the following. With this being said, we can now rewrite our general solution into a condensed form. So the general solution to the differential equation d vector x over dt equal to a vector x, where A is our n by n matrix right from the beginning, of this eigenvalue of matrix A. So that A is right here, corresponding to this A. The general solution to this system is actually given by this expression. Vector x is equal to, actually maybe I'll draw in this line. Vector x is equal to u lambda t, oops, vector c. Okay, now how do I see this? Well, actually pretty simple. If you see this, all you have to do is really think about that would be the matrix U multiplied by its diagonal matrix multiplied by vector C, which is C1, C2 to Cn. So when you multiply this together, guess what happened? What happened is there will just be C1 times E lambda 1t plus a whole bunch of 0. So therefore become U multiplied by E to the lambda 1 C1 E to the lambda 1t. And then the second row multiplied by column will just become C2 e to the lambda 2t, and so on and so forth until C sub n e to the lambda nt. And now since you using each of the vector eigenvector as columns, you can then think of U as being this. And so when you multiply this together, it's basically equal to this. Which is exactly how we expect our solution to look like when we have n that many eigenvalue with n that many corresponding eigenvector. It's the same exact formula that we wrote right here. Okay, notice this is the exact same formula, except that when I wrote it down there, I have to take the last term and put it underneath because I ran out of room. So now you have a new formula that you can memorize that would kind of summarize this eigenvector solution, eigenvector, eigenvalue solution. Now come the next question. What if we have some kind of initial condition? Well, so let's see. So number 5. What if we are given the initial condition? Vector x of 0 equal to some constant vector x of 0. What will happen? Well, then simple. What we're going to do is try to solve for c given this condition. So let's see if we can do this. So our solution is vector x equal to u lambda t vector c. So if I now put in this condition vector x of 0 equal to x of 0 would imply that x sub 0 is equal to u lambda 0 vector c. So notice that would mean that the output vector x is actually x sub 0, while when we plug in 0 for the input, which in this case is a t variable. So therefore I replace the t with 0. Now, think about what happened if I do plug in 0 for t in our lambda sub t matrix right here. That will mean that will become eta 0, eta 0, eta 0 along the main diagonal. And that would actually turn it into the identity matrix. So something important to understand is that lambda sub 0 is always equal to the identity matrix. So therefore, vector x would equal to u times the identity matrix times vector z. And that just simply means that the matrix u multiplied by the vector z. And so now if I want to find c, what do I do? Well, notice that matrix u is formed by linear independent eigenvector. And therefore, we can safely assume that u must have an inverse. And with that being said, u is invertible. Therefore, u inverse exists. Therefore, if I want to find c, what I'm going to do is simply say that c must equal to u inverse of time vector x sub 0. That gives us a way to find all the arbitrary constant. It's by simply taking the inverse of the eigenvector matrix and then multiply by the initial condition, provided that the initial condition is at 0. With that being said, now we can actually state the following. Let's say we're given d vector x over dt equal to a vector x with vector x at 0 is equal to vector x sub 0. Then the solution to this system is given by this formula. I know some of you are thinking like, well, wouldn't u times u inverse become the identity matrix? Yes, they would. The problem is, remember, matrix multiplication is not commutative. You're actually not allowed to rearrange this multiplication except exactly the way it is. So therefore, you have to kind of leave it the way it is and have to multiply them in order. So therefore, you cannot use the fact that u and u inverse cancel each other to actually simplify this further. It's really not allowed. Now, what if you have the same exact system, but instead your initial condition is given at a specific value called t sub 0. How does that screw up the solution? Well, actually, it doesn't screw up the solution by a lot. It actually just changes to this. The solution to this system with the initial condition is actually this. All I have to do is scale the t by translating it to t sub 0, then everything is okay. So these are the two formulas that you can memorize and then use them to actually solve a system of differential equation using the eigenvalue and eigenvector. So let me see if I can show you an example using this. So we're going to use an example that we have done before, so that way it's easier to go through the process. So let's say we have this system right here. So we already know the following. We already know that this has an eigenvalue, lambda 1 is 3, and eigenvalue 2 is -1, along with eigenvector, which is 1, 2, and second eigenvector, which is 1, -2. So let's say we can go through this process and see if we can come up with a similar solution like what we did before. Let me see. We actually should have the answer to this thing somewhere up here. Okay, let's see. Nope, not this one. This one right here. So this is how our solution come out to be at the end. So hopefully we gotta wind up having something similar. Okay. So actually, you know what? I'm gonna do this. Okay. Let's do this again. No copy. And I'm going to try to paste right here. There you go. Alright, that's close enough. So here's our solution. Oops. We know that this is our solution. So what I want to do is to first show you what happened if I want to find C1, C2. So let's say we're given the following condition. Let's say vector x at 0 is equal to vector x of 0, which is the vector 2, 3. So I can now try to solve for this. So therefore, this will imply that 2, 3 is equal to C1 times 1, 2 plus C2 times 1, -2. Okay, because e to 0, t is 1, so therefore it's gone. So therefore, tell me that is 2 equal to C1 plus C2, and 3 is equal to 2C1 minus 2C2. So that's a very easy system to solve. I'm going to go and multiply the top one by 2. So it's 4 equal to 2C1 plus 2C2. And the bottom equation stays the same. And if I add them together, these two cancel out. And seem to me 7 equal to 4C1. So C1 should equal to 7 over 4. And if C1 is equal to 7 over 4, C2 should equal to 1 over 4. So that way they will add up to 2 when I add them together. So therefore, we know that our solution, in this case, subject to the initial condition, should equal to 7 over 4 e to 3t 1, 2 plus 1/4 e to -t times 1, -2. So to properly write this out, I would say this means xy is actually equal to 7 over 4 e to 3t plus 1/4 e to -t, and then 7 over 2 e to 3t minus 1/2 e to -t. So that's my solution with the initial condition. So now what I would like to show you is to use this formula to now, we can now check our solution using this formula. And hopefully this would give me the same exact answer, and therefore I can now use this to actually solve the system instead. Now, unfortunately, my time kind of ran out. It's already 30 minutes already. So what I'm going to do is we're going to do this on our next video. All right, I'll talk to you guys again soon. Okay, bye-bye.